SVG was not made for humans. That is clear. In this video, I'll show you how to create SVG images programmatically and in a fun way. My name is Max Generis, and in this presentation, I'll break down some tools and techniques I would use to create Kenny Vaden's piece of generative art you see now on screen. In the first part of the video, I'll be focusing on recreating the Kenny's piece, and at the end, I'll show you a cool twist of it. The final source code will be made available and linked in the description. For development, I'm using Vt.js, which will compile, serve, and refresh the page at the save time. The starting point is a basic HTML file to which I attach a script element linked to my source code. Let's inject into the page some handwritten SVG and see what we got in the developer tools. As you can see, there's an SVG node there with some default width and height. We could go on the same way to the end, but the code would soon become unreadable. This is why I chose the hiccup notation. A hiccup node is basically an array with the first element being the tag name. The second optional element is an object holding the element's attributes followed by any number of child elements. To serialize the hiccup representation of the SVG, I'm using the hiccup package created by Carsten Schmidt and which I'm importing here. Let's now write a basic hiccup representation of the SVG injected earlier. Now I'm adding the width and height attributes. You can see in the developer tools how this is reflected. In order to do our calculations, I'm defining some constants for width and height and use them to build the SVG tree. You can see that our image is now filling the screen. I'm also pasting the namespaces for good measure. I like to have my 0, 0 coordinates in the center of the image. This is why I add now the viewbox attribute and set it up to reflect this. The viewbox takes the top left corner and the width and height of the region. I'm abusing a lot of string interpolation. I think it's amazing. I'm adding now a rectangle to fill the screen. I'll make it red to start with, but I'll change the color later. This is going to be our background. The X and Y coordinates will be for the left top corner and set to -half width and -half height. The fill attribute is specifying the color of the rectangle. Now it's time for the meat of a generative art algorithm, the randomness. The first function I'm defining, our float, return a random floating point number between min and max arguments. The same goes for the rint function, the only difference being that it returns an integer value. The third function, or pick, is taking an array as argument and returns a random element from it. Let's now define our palette. I'm starting with some hard-coded hues array. Later, I'll generate a random one. Based on a randomly picked hue, I create a color using the HSL CSS function to replace the original red for our background. I want the color to be dark, so I'll keep a low luminosity argument. You can see the color changing as I repeatedly save the file. The next step in reproducing Kenny's image is to define a grid. For this, I'll implement a few array generating functions. The rep function takes a number n and a function arguments and returns an array of length n containing values returned by applying the function argument over the index. Let's use this function to generate our hues palette. The length of the palette will be a random value between 2 and 5, and the values will be random numbers between 0 and 360. Our next array function will be range. The range function will take a min, max, and step arguments and produce an array of step distance numbers between min and max. The third array function is grid, which takes two arguments, columns and rows, and produces an array of tuples of indices for each column and row in the range 0 columns and 0 rows. Now is time to declare the grid cell size. I'll make it a random value between 30 and 60. Based on the cell size, S, I'll calculate the number of columns and rows fits in 94% of the image width and height. I used 94% in order to leave some border to the image. The number of columns, for example, is the integer part of 94% of the width divided by the cell size. After all this calculations, it's time to add some cells to our image. To generate the cells, I'm using the grid function and map the result to our hiccup nodes. For starter, I'm plainly adding some rectangles directly positioned at the column and row coordinates. These being indices, it will crowd all the rectangles in the center. I'm stroking them with blue in order to see if all is good and I have no errors. All looking as expected, I am now factor out the cell part in its own function. The function is taking the column and the row indices and will return a complete cell. First thing is to get the rectangles at the proper position. For this, I calculate their x-coordinate as column times the size of a cell. I do the same for y-coordinate. As expected, the grid cells are drawn from the center of the image. In order to place it properly, I need to subtract half of the grid width and half of the grid height from the x and y coordinates respectively. Let's add some colors from our palette to the grid. The h variable would be the hue value for the current cell and will be used for all the elements drawn. In order to draw both the rectangles and their halves, I'm going to calculate the four corners positions and store it in rectPoints as variable, and replace the rect element with a polygon element. All working as expected, I'm replacing the blue color with a color generated with the same HSL function I used previously for the background. This time, I'm making it a lot brighter and I remove the default black fill. The cell element being a lot more than the rectangle already added, I am nesting everything under a G element, which stands for SVG group, and move the stroke attribute at the group level. Happy so far? I am now calculating the triangle points by randomly eliminating a corner of the rectangle. To spliced array method is returning an array copy after the splice operation is performed. The index of the corner will be picked randomly and the number of elements removed is 1. As you can see, all is started to take shape. Let's revert back to our rectangle and add another polygon for the triangle points. As opposed to the rectangle, the triangle is filled with color. I introduce a slight variation in the saturation and luminosity random ranges. The last design elements that are not yet added are the horizontal and vertical lines. I'm storing in the line count variable a random number between 7 and 20. In order to add the lines, I'll call the rep function and pass to it the logic to compute the line positions. The horizontal lines start at X position and end at X plus S. And on the vertical axis, go from Y to Y plus S at an interval of S divided by the line count. Now all cells have the horizontal lines. In order to skip some cells, I invoke the rep function, having the first argument randomly picked from an array of 0 and line count. The more zeros I add, the less frequent the lines will be drawn. 1 in 3 instances. Look nice. Let's do the same for the vertical ones. One last fine touch to reach our goal is to get rid of the pointy corners of the triangles. You can see them if we zoom in. To get rid of them, we need to change stroke line join attribute to round. I also change the stroke line width of the rectangle and triangle. To get close to the original piece, look, I'm setting rectangle line width to 1.2, horizontal lines, thickness to 0.5, and the same for vertical ones. Looking good, right? Now to add the cool twist I promised at the beginning, I add an animate transform node under the cell group. This is used to animate transform attribute of the element. I set type to rotate from 0 degrees to 360 degrees, duration 4 seconds, and repeat count to indefinite. Now all the cells are rotating around the center of the image. To make the cell rotate around its own center, we need to add the transform origin attribute to G node and set it to X plus half size and Y plus half size. Isn't it cool? I hope you liked this video and learned some things. See you next time.